Okay, imagine this. What if you could read, say, the tiny letters on a coin, but from like over a kilometer away?
That sounds like science fiction almost.
Right, but not with some massive telescope, but using a completely different way light behaves. Something called intensity interferometry. It's about getting incredible clarity, but not just by zooming in.
Exactly. And that's our deep dive today. Intensity interferometry. It's this fascinating technique astronomers develop for staring at stars. But now researchers are figuring out how to use it to image things, well, right here on Earth.
And we're pulling this from a great piece over on physics.com. They really break down how this astronomical tool is being turned towards, everyday imaging
It's
problems.
a fantastic adaptation.
Now, for you listening, especially if you're maybe prepping for the UPSC exams, you'll want to lean in here. This kind of tech, it could have huge implications. Think surveillance, remote sensing, security.
Definitely feels relevant to governance and tech advancement.
Understanding the basics here could really give you an edge for prelims, mains, that whole science and tech section. But honestly, for anyone listening, it's just mind-bendingly clever science.
Absolutely. So let's unpack this astronomer's trick on Earth. The core idea in this research, they illuminate a target with several laser beams.
Okay, lasers, got it.
Then they use two separate, pretty small telescopes to catch the reflected light. But here's the key thing. They're not trying to get a perfect image from each telescope.
Right. It's not about magnification in the usual sense.
No, it's about comparing the tiny, rapid changes, the fluctuations in the intensity or the brightness of the light hitting each detector.
So how bright the light is and how that brightness flickers, basically, at two different spots.
Exactly. And by analyzing how those flickers correlate or match up between the two detectors, well, that's where the magic happens.
And the results they got. The article mentioned something pretty stunning.
Oh, absolutely. They managed to image letters just millimeters wide from 1.36 kilometers away.
Millimeters.
Huh.
From over a kilometer.
Yeah. And get this. The resolution was 14 times better than what just one of those telescopes could manage on its own.
14 times. Wow. So you go from maybe seeing a blur to actually reading something.
Precisely. It highlights this crucial difference between intensity interferometry and the more, let's say, common amplitude interferometry, like they use in radio astronomy.
Okay. Amplitude interferometry. That's where they combine signals from big radio dishes, right? And they have to line up the waves perfectly.
Exactly. They need to preserve the phase, the peaks and troughs of the waves very carefully to add them up constructively. Intensity interferometry. It kind of throws that phase information away.
It doesn't care about the phase.
Nope. It only cares about comparing those intensity fluctuations, how the brightness is randomly changing at the two detectors.
So instead of smooth waves, you're looking at the random little ups and downs in brightness and how those ups and downs match up between the two detectors.
You got it. By looking at the correlation of those fluctuations over time, and how that correlation changes as you move the detectors further apart or closer together, you can actually reconstruct spatial information about the source.
Okay, that's clever. You're building a picture from how light twinkles, essentially.
It is quite clever. Now, why these correlations happen, that can seem a bit, well, counterintuitive. There are quantum explanations involving photons.
Uh-oh. Quantum. Keep it simple.
Okay. Think of it like this. Photons from the source arrive at the detectors. Sometimes, due to the nature of the light source and quantum effects, they tend to arrive in bunches or pairs. So you see a simultaneous spike in intensity at both detectors.
So light particles clumping together, sort of?
In a manner of speaking, yes. It's called photon bunching for thermal light. This effect gets weaker the further apart your detectors are. That dependence on separation is what lets you map the object.
Interesting. And this isn't totally new, right? The article mentioned it goes way back.
That's right. Hanbury, Brown, and Twiss first demonstrated it back in 1956. Astronomers used it to measure the actual angular size of stars, which is incredibly difficult otherwise.
So why isn't it used all the time if it's been around since the 50s?
Well, the main issue is signal to noise. These intensity correlations are usually very, very weak compared to background noise, especially for faint astronomical sources. Amplitude interferometry, when you can preserve the phase, generally gives a much stronger signal.
Okay, so it works, but it's often faint. What makes it suddenly so useful for imaging things here on Earth, then? Why now?
This is where it gets really interesting. Intensity interferometry has this kind of unexpected advantage in what you might call disordered environments.
Disordered, like messy.
Exactly. Situations where the light gets scattered and scrambled. Think about trying to see clearly through atmospheric turbulence, that shimmering effect over hot pavement.
Yeah, impossible to get a sharp view sometimes.
Or imaging through biological tissue, which also scatters light like crazy. In those cases, the phase of the light waves gets totally messed up, which makes amplitude interferometry really, really hard, if not impossible.
So the very thing that messes up the normal method, the scrambling of light, this intensity method, can actually work with.
That's the key insight. It's less sensitive to that phase scrambling. It just looks at the intensity fluctuations, which still contain information even after the light has been scattered.
Okay, turning a bug into a feature. I like it.
Yeah.
So how did these researchers apply this on Earth? What was their setup?
They built a system specifically for remote imaging through the atmosphere. It involved 2 telescopes, an infrared laser system, all mounted together.
An infrared laser.
Okay, now you'd think a laser gives you this really nice, clean, coherent light, right? Perfect for imaging.
You would think, but here's the twist. For this technique, using perfectly coherent laser light is actually a problem.
Wait, what? Why? Because the intensity fluctuations you'd measure would mostly just be the laser's own internal noise. It's called shot noise. Basically, random fluctuations in photon emission. That noise would drown out the subtle fluctuations carrying information about the target.
Huh. So the laser's own flicker hides the flicker from the target.
Precisely. So the researchers did something, well, really ingenious. They took their laser beam and split it into 8 separate beams.
8 beams, okay.
And this is the clever bit they made. Each beam travel a slightly different path, deliberately introducing random phase shifts into each one before they combine to illuminate the target.
They deliberately made the laser light messier, less coherent. That sounds completely backwards.
It sounds totally counterintuitive, I know.
Yay.
But by creating this incoherent illumination, this controlled randomness, they essentially suppressed the laser's own shot noise relative to the signal. It allowed the intensity correlations from the target to actually become detectable.
Wow. Okay, that is seriously clever engineering. Reduce the coherence to see better. Mind blown. So what did they actually manage to image with this scrambled laser light setup?
They set up targets about 1.36 kilometers away. These targets were letters, like the letter N or U, made of reflective material, and they were only 8 millimeters wide.
Tiny, like fingernail size from that far.
Pretty much. And to build the image, they did 2 things. They varied the distance, the baseline, between their 2 receiving telescopes from just 7 centimeters out to 87 centimeters. And they also rotated the target itself, step by step, through a full 360 degrees.
Okay, so moving the detectors and turning the object.
And at each step, they measured the reflected light, calculated those intensity correlations, and then used algorithms to put all that correlation data together to reconstruct an image.
And the resolution they achieved.
They got down to 3 millimeters resolution.
3 millimeters. Compare that to what could a single telescope see?
A single one of their telescopes at that distance would have a theoretical resolution limit of about 42 millimeters.
So 42 millimeters versus 3 millimeters. That's huge. You wouldn't even make out the shape of the letter with the single telescope.
Not clearly, no. It's a massive improvement, really demonstrating this works in practice through the atmosphere.
Yeah.
And they're not stopping there.
What's next?
The article mentions they plan to improve control over the laser light, maybe refine that incoherence effect even more, and they also want to bring in deep learning.
AI for image reconstruction. Makes sense. That could probably pull out even fainter details.
Could be very powerful. And they have specific applications in mind, too.
Like what?
One big one mentioned is tracking space debris, all that junk orbiting Earth.
Right, that's a growing problem. How would this help?
Well, space debris doesn't emit its own light. So you can shine lasers on it from Earth and use this technique to get much better information about the size, shape, maybe even rotation of these objects than you could with, just say, radar or conventional optical imaging.
That could be really valuable for collision avoidance. Any other ideas?
The article quoted some other experts, too. Shoria Arav from Sorbonne University called it a significant technical advancement for seeing distant things that don't glow on their own. He even suggested maybe monitoring insect populations over large areas.
Wow, like counting bugs from a kilometer away.
Potentially.
Yeah.
And Ilya Starshinov at the University of Glasgow was impressed by the clever incoherent light system and just the basic feat of seeing millimeter details at kilometer ranges.
Okay, so let's sort of wrap this up. We've got this technique, intensity interferometry, born from astronomy.
Looking at stars.
Now cleverly adapted for Earth. using multiple kind of randomized laser beams to overcome noise problem.
Yep, the incoherent illumination trick.
And achieving this incredible jump in resolution, seeing millimeter details from over a kilometer away.
It's a really powerful demonstration.
And for you listening, especially our UPSC aspirants, this is a perfect example of how fundamental physics finds new life in technology with really significant potential implications. Surveillance, environmental monitoring, like that insect idea, maybe even new security tech.
Definitely something to keep on your radar in the S&T space. It touches on optics, lasers, signal processing, potentially AI, lots of relevant areas.
It really makes you wonder, doesn't it? Is this like the first step towards a whole new way of seeing, understanding our world in much finer detail, pushing what we thought was optically possible?
It certainly feels like a boundary being pushed. It shows that even concepts from decades ago can be reimagined with modern tech to solve new problems.
Absolutely fascinating stuff. So if you found this deep dive as cool as we did, do give us a like, subscribe if you haven't, and definitely drop a comment. Any questions, thoughts on where this tech could go, let us know.
We'd love to hear from you.
And remember, the full details underpinning this are in that great article over at physics.com. Definitely worth a read if you want to go deeper. Thanks for tuning in to this deep dive.